So this is the introduction to chapter 24. This is kind of redoing things that we did in class in a slightly different way. So if you were there at that lecture, then this is just supplemental material. You can see it or not. You've already got most of the concepts. So the idea of chapter 24 is we are introducing the idea of capacitance. And capacitance, just like the word sounds, means the capacity to hold charge. So it's a specific application. It's just a different way of thinking about things that we've already done. You guys have already done this. So, for example, we can look at the idea of just two plates, and these two plates are both conductive sheets. So they're big conductive sheets. The spacing between them is much smaller than their area. So we essentially, mathematically, we regard them as infinite planes of charge. And right at the moment, they're two conductive planes, but they don't have any charge on them. Does that mean that they do not have the capacity to hold charge? No. If we put an electric field here, we could deliver some charge to each of these things, each of these objects. So there's the idea of capacitance is that there is some intrinsic property of this geometry that will hold a certain amount of charge depending upon how much electric field is around there. So what we're looking for is something that will be a function of voltage, but will not be a function of what's the right? That's not quite the right thing, but will not change for this material. It'll be the same for this object regardless of what voltage is applied to it. And it turns out that we can find such a thing, and it makes sense that we find such a thing. You can imagine if we rubbed a rod and just put positive charge here, then it would hold that amount of positive charge. If we rubbed a rod and put more positive charge there, it would hold more positive charge. Okay, all right, so the other thing that we are going to talk about, that we aren't really talking about, I think, till the next chapter, your book doesn't talk about it much, is batteries. So the only thing we need to know about batteries, this is the symbol for battery. The only thing we really need to know about battery is that you can regard it as an object that provides a certain amount of potential difference regardless of what else is going on. So regardless of how much charge is leaving a battery, it will continue to supply that same amount of charge, or no, I don't want to say it that way. It will continue to try to produce charge so it always maintains that potential difference. There we go. That's the right way to say it. So what we usually will write this as the plus being equal to V, the minus being equal to 0. So if we look at here and we say, all right, well, this is just, review again for those who were in class, but anytime you just see a line in the schematic of a circuit, it just represents a conductor. So you know what happens with a conductor is the positive charges are free to move. There's an electric field because there's a potential difference, because there's charge, all three of those being the same thing. And so that charge will try to repel itself and get as far away as possible from here. Well, because the battery can continue to supply new charge, what that effectively means is you're going to keep putting charge all the way over here until there's no net force on these charges here. Just like has always been true since we talked about conductors way back. What are they going to do? They're going to move until the net force is 0, or that is the forces are balanced out. Well, when is that going to be? That's going to be when the voltage here equals the voltage here. So that's what happens with a circuit. And same thing here. The voltage here is 0, and this will, I know it's kind of funky to say 0, but I guess we can kind of stick with it. But the voltage here will always be the same, okay? Because this is a conductor, and charges will move as long as there is a potential difference between here and here. But in a conductor, charges are free to move, therefore they will move until they balance out the potential. Okay, so what we end up with is net positive charge here, net negative charge there, and now we're just going to do things that we have already done. You already know that these will have a constant electric field between them, and you know that the electric field is defined as the negative of the gradient of the voltage with respect to the direction. The direction here, the symmetry is all for here, so we are talking about the voltage change from here to here is just V, so this is minus V, and what is the distance there? It's just D, so that is now the specifics for what we have here. And the minus sign just means that, well, look here. Here is plus V, here is 0. So if we were to go in the plus direction, then this minus V over D would be pointing in, I'm sorry, plus V over D would be pointing in this direction. Minus V over D just says we're pointing in this direction. And the reason we choose that is just for consistency. Remember, we could have chosen positive charges to be negative charges. You know, it's just, we're just making this definition to be consistent with everything else that we have done so far. So that's why we have this minus sign. And it's just about direction, right? Okay, so minus V over D, and we know in this case it's in this direction, which it doesn't really matter to us right now. But, okay, so... all right, so we have that expression for the electric field. This is the magnitude of the electric field. And what else do we know about this electric field? Well, you guys remember we've done this thing with the Gaussian surfaces, where we can do this deal, where we can show with two separate Gaussian surfaces here. This one is going to have a sigma over 2 epsilon 0 in this direction. This is a plus 2 sigma over 2 epsilon 0. Meanwhile here, you know, we get a minus 2 sigma, minus sigma over 2 epsilon 0. But what does that minus mean? This is dA right here, so minus just means we're opposite the direction of dA, and therefore, how do these two add up together? They get to be sigma over 2 epsilon 0. I'm sorry, that's the whole point, is there's no 2. Sigma over epsilon 0. Okay, so now we're just going to set these expressions equal. We have sigma over epsilon 0. I'm not going to get rid of the minus sign just because I'm only talking about magnitudes right now, so it doesn't matter what the direction is. If we kept this minus sign, the only information it would give us, it would tell us which side of this had the plus charges and which side of this has the negative charges. But we aren't concerned about that right now. We're just concerned about the magnitude of charge that's going to be stored here. So we know that this is true. Sigma over epsilon 0 equals V over D. Let's go ahead and multiply both sides of this by A. So now we have sigma A over epsilon 0 equals sigma, there's no sigma there, equals V A over D. Well, what is sigma times A? A is the entire area here. Sorry, I didn't explicitly mention that. A is the entire area of one face, so sigma A is equal to Q. So we have Q over epsilon 0 equals VA over D. Well, now we're getting close to something which I said we were aiming for. We were looking for something that would indicate how much charge could be stored on an object, and we expected it to be proportional to the electric field or the potential difference. And so we end up with Q over V equals epsilon 0 A over D. And you will note that, well, no, there's no noting. I'll just tell you that this right here, this quantity, Q over V, we define this as a new parameter C. I'm just going to write it up here. So C equals Q over V, but it doesn't equal, it is defined as Q over V. Okay, so we make up this new term because we will find it convenient to express this as the property of a material. This C is the property of a material, and it allows us to simplify all the rest of the work. And really that's why we're doing this, and I mentioned that we're now kind of moving to the simpler portion of this course. Not that there's not lots of new stuff and plenty of, it takes time to get it, but now what we're doing is we're taking all the hard work we did on the previous chapters and we're saying, what are the consequences of this, and can we make this easier to deal with on a daily basis, rather than trying to integrate all these charges up here and integrate all these charges here and then determine what the electric field is there. We're trying to do things in simpler fashion. This is the beginning of our move to that. We've just discovered this, but we discovered this with all the tools that we had over the previous chapters. Okay, this is what this chapter is about.